I left off with the Seiberg-Witten. So remember, the function goes from h2 of z. In Tom's talk, it will be substituted by spin c of x, and there will be a relation between the two. I will not spend time on that. Spin c structure always determines the second cohomology class. Not every cohomology class appears, only the characteristic ones, and the cohomology class does not determine the spin c uniquely unless there are some other assumptions, like there is no two-torsion or something like that. So it's a white lie, what I'm doing, and it's okay. And then, yeah, well, you know, I do. And basic class, K basic class, if the value is non-zero. And I quoted two vanishing theorems. When the B2 plus and the B1 have the wrong parity, then somehow the invariants are zero on the node. And if the manifold decomposes in a special way, that both, it's a connected sum, and both components have positive B2 plus, then invariant vanishes. And there was an unvanishing theorem for symplectic manifolds, and symplectic just means that there's a very special truth form. And the most important property, or the very important one, is the following theorem, which goes back to Peter Kronheimer and von Rofka, and it's called the adjunction inequality. Goes as follows, and there are some extensions, but I will just take the most basic one. So suppose that X is, as always, a closed oriented four-manifold, oriented with B2 plus of X bigger than 1. So this assumption will be clear when Tom will define the Seiberg-Witten function. As I stated at the end of the last lecture, it's well defined only under this assumption. And if it doesn't hold, then we have to do some more fancy thing, which I will now avoid. And suppose that there is a two-dimensional embedded surface, also closed and oriented. Such that Q of X of sigma is positive. If you are really careful, this expression needs a little bit of an explanation. So sigma is a closed and oriented surface. It has a fundamental class. Sigma is the image in H lower 2 of xz, the fundamental class of sigma. And I insisted to have the Q of the second cohomology, although these guys are elements in the second homology. But you have to remember that there is Poincare duality, and for a four-manifold, H lower 2 and H upper 2 are just isomorphic. Independent of simple connectivity or anything, they are just for closed four-manifolds. They are just isomorphic, and so it will give me the opportunity to jump back and forth. Sometimes I write Poincare duality, sometimes I don't. Okay, so these are the assumptions. And if K is a basic class, remember basic classes are from second cohomologies, then we have an inequality. And the inequality is the following. We take twice the genus minus 2. This is just secretly the negative of the Euler characteristic of the surface. And this is always at least the self-intersection. Plus the value of the basic class on the homology class in absolute value. Okay, so we can view it in two ways. The genus somehow bounds this expression from above, or you can say that the homology class of sigma somehow bounds its genus from below. So this is a homological quantity, this is a homological quantity, the cohomology evaluated on the fundamental class. So this side depends only on the homology, and this is what sort of describes the geometry of the surface. Why is it called a junction inequality? Well, so
greater than or equal.
Say it again.
Greater than or equal to.
Here?
No, the assumption.
Yeah, so I can do that, but then we have to worry a little bit about spheres or something. Right? Anyway, yeah, we can put that. So where does the name come from? So suppose that X is a complex surface. So the tangent bundle is not really an R4 bundle, it's a C2 bundle. And C inside is a complex curve. So a very special two-dimensional submanifold. And it's a closed complex curve. As we discussed, if it's complex, it comes with a canonical orientation. And then we notice that if we take the tangent bundle of X and restrict it to C, then this bundle, this is a C2 bundle over the curve, it will decompose into the tangent bundle of C plus the normal bundle of C inside X. Right? So the usual picture, C, and then we take the tangent bundle of X, and there are these directions along C, and then there are the normal directions. And now this is exactly the splitting which Tom discussed like 2 hours ago, and then he took the second Seiberg-Witten class. Now we take the first Chern class because this is a complex two-plane bundle, this is a complex line bundle, complex line bundle. So we take C1 of TC, and by the Whitney formula, this is just the same as C1 of TC plus C1 of mu C with H upper 2 of C with Z coefficients. Okay. So we can integrate it against C, and so we get that C1 of TC on the fundamental class is C1 of TC plus C1 of mu C. And now it needs a little bit of a thinking what it is. The first Chern class is equal for a curve, for a complex curve, it's just the either class. So this integral gives you the either characteristic of C. This gives you the set intersection. And this is just C1 of the tangent bundle evaluated on C. And if you reorder appropriately, you just put this on the other side and this goes to the right, you get that minus chi of C is equal to C squared minus C1 of Tx evaluated on C. So in some sense, basic classes can be viewed as the extension of the first Chern class of complex surface to manifolds which don't have complex structures but still admit the Seiberg-Witten invariants, and whenever it's non-zero, then we have this inequality. As a remark, if you have a complex surface, well, with B2 plus bigger than 1, then the first Chern class will be always a basic class. This will be exactly the class I referred to in the symplectic case. So this formula, this is called the adjunction formula. And if you want to be very vague, then you say that Seiberg-Witten theory is just an extension of this holomorphic complex geometry to every four-manifold. Okay, so what we would like to do is to study smooth four-manifolds. The question is, what shall we study? What are the properties which are important? And there is a very short answer: we don't really know. Yeah, not yet. So what is our hint, or what do we feel to be studied? Well, in 3D, so why three-manifold? The most important information is its fundamental group. And by Perelman's work, we know that for irreducible three-manifolds, essentially the fundamental group determines the three-manifold. So what we have to do in the three space is to study loops and then turn it into a group and then understand the manifold from there. Well, a natural next step would be that in 4 dimensions, we would like to understand surfaces in the four-manifold, and this is what we will focus on from now on. So X4 four-manifold, study surfaces. So here is a definition. So consider the following function defined on the second homology. So we take a second homology class and then associate with the minimum of all the genera, sigma closed oriented, smoothly embedded, by embedding I, so that I lower star of the fundamental class is exactly off. So what do I mean by this? Here is X. We pick a homology class. We consider a lot of different surfaces, and we consider their fundamental class embedded in the homology, and we select those which hit exactly what we are concerned about, and we just take the minimal genus. And we hope that this property, this function, will tell us something important about the four-manifolds. I should point out that there is a very similar construction in three dimensions. You just take homology classes and represent them by surfaces and take the minimal genus or complexity, and this leads to the Thurston norm, which is a fantastic gadget, and it has a nice structure. This is also a fantastic gadget, and it doesn't have a nice structure. That's a problem, but we have to live with that. Okay, so here is the first here is a theorem. This used to run under the name of the Thom conjecture. And this is now a theorem of Kronheimer and Brovka. And this gives a concrete and absolutely precise description of this function for one particular four-manifold. So for CP2, for x equals CP2, the complex projective plane, G CP2 on D times H, where, so there is a formula coming, and H is the generator and D is a non-zero integer. It's just 1/2 d minus 1 times d minus 2. So this just tells us that this function can be computed. It's sort of a little bit misleading because there is only another handful of manifolds where when this manifold when this function is actually computed. I don't know whether this will be proved. Maybe, or maybe not. Yeah, who knows?
Maybe something new.
G is also known for S2 process 2, CP2 connected some CP2 bar, and practically that's all. There are very few other manifolds. Maybe you can do it for T4, and that's it. The point is that notice we do have a bound here based on the basic classes, but only for homology classes of non-negative square. In CP2, luckily that consists of all the homology classes. In S2 process 2, this is not true anymore, but there is a trick. You can flip the orientation of S2 process 2, and it's still S2 process 2. So, and the same holds for this. Notice that these are the two S2 bundles over S2. So there are a few other very simple four-manifolds where you can play that trick. In others, say you take CP2 and take the connected sum with two CP2 bars, then we don't know exactly what happens with classes with negative self-intersection. So although this is a fantastic result, but it holds only on a very small collection of four-manifolds. Okay, so this is our main goal, to sort of understand the more we can about surfaces in four-manifolds, and hopefully this will shed some light on their smooth structures. And in order to do that, I need to introduce a few technical tools, and this is what I would like to do next. And this is the blow-up. This is the blow-up procedure, and so it needs a little bit of preparation. So consider tau to be the following space. We take pairs P and L from C2 cross CP1. Remember, this is just C2, and CP1 is the space of lines in C2 passing through the origin, and the condition is that P should be L. Right? P is a point in C2, L is a line in C2, which is a point in CP1, and this is the condition. Well, this is not so hard to see that if we use coordinates in C2 and homogeneous coordinates in CP1, so this is still in C2 cross CP1, then this condition that the point should be in L is the same as saying that the slope should be the same, which is sort of a little bit off if y or v is equal to 0. So instead we just write it saying that xv should be uy. So this equation gives us a submanifold inside this product. This is a complex manifold. It gives us a complex submanifold. It takes a little bit of thinking to show that indeed it's a smooth submanifold. You just have to apply the implicit function theorem. Okay, so this is not so easy to imagine, but if you want to have a good picture, you can just run the same procedure over the reals, and then we will have P and L in R2 plus RP1. And so this is much easier to imagine, because RP1 is just a circle, and R2 can be imagined like a little disk. So you have a circle worth of disks, and then over every point of RP1, over every L, you just take all the points inside that L. So you have circle cross the D2s, and in every D2 you take an interval which is sort of rotates, and when you go a full circle, it exactly turns 180 degrees. So this is what we call the Möbius band, right? So this is the Möbius band. If you are confused, then you just go to the back of this building, and there is this staircases, and then you just take one turn, and that's what it is. It's very visual, and there are two functions from this space. Of course, it's in a product, so you can project it to the first coordinate or the second. So this goes to C2, and this goes to CP1. And it's very easy to see what are the fibers. So if you pick a line, then over that line, you just have, so you fix L, you take all the P's which are in this line. So the fiber of projection number 2 is just a complex line. So this is a complex line bundle. Actually, this is the tautological line bundle over CP1. So this is a complex line bundle over the sphere. This is a very well-studied object. This function is a little more interesting because here I fix P. So the question is how many lines pass through P, of course from CP1, so these are all the lines which pass through the origin. So if P is not equal to 0, so what are the fibers? If P is not equal to 0, then of course there is a unique line determined by the origin and P, so the fiber is a unique point. What happens if P is equal to 0? Well, if P is equal to 0, then how many lines pass through the origin and the origin? Well, every line which passes through the origin, so then it's just CP1. So this is kind of a strange function. It's one-to-one away from the origin in C2, and over C2, there is, instead of a point, you have a balloon, a CP1. This is why it's called the blow-up. You just blow air into a point, and it becomes a CP1. Once again, if you have hard time visualizing it, then try the real picture where the blow-up means that you substitute a point with a circle. And again, if you are confused, you just go back in the building and then you visualize that. Okay, so that's fantastic. We can change a complex manifold by taking a point and inserting, instead of a point, we insert an entire sphere. So can implement this on any complex chart of a complex surface. Or actually, we can take a smooth manifold X, pick a point, take a neighborhood which we know is homeomorphic to R4. We treat R4 as C2, and we just blow up this point, we just substitute with a sphere. The question is what happens with, say, the characteristic numbers, the fundamental group, either characteristic signature. And this is not so easy, but not completely obvious. So here is another observation. Take CP2 and fix a point, P. So this is my CP2, fix a point P, and a line L. And line L such that P is not an L. So a line and the point outside of that, and consider all the lines through P. So take LT lines through P. This will give, so this will sort of sweep out the entire CP2. You know, we know that every two lines which are distinct intersect in one point, and the LTs should be distinct from L because L doesn't contain P, while all the LTs do contain P. So this will be a sweep out of the entire CP2. This gives the fact that CP2 minus P also fibers over CP1 with fibers just complex lines. You know, these lines are projective lines, and once you delete P, they will become just complex lines. So this is also a complex line bundle. And now comes a little bit of a yoga to understand that this complex line bundle is actually the same as that tau projected to CP1. With a little bit of an issue, the orientation comes out wrong. So here's a fact which can be checked by computation, that CP2 minus a point with the opposite orientation comes out to be equal to tau. That means that when I apply this procedure, consequence, blowing up x at the point little x is the same as taking x and connect some with CP2 with the opposite orientation. Okay? So when four-manifold topologists talk about blowing up, this just means that we, instead of x, we just consider x connected some with CP2 bar. Notice that it comes with extra features, namely that we just try to draw this second map. So this is my C2, there is tau over it. If you have two lines passing through the origin, then when you lift the lines up there, they will sort of miss each other. More precisely, if you have a line L, this is projection number 1, and you take the inverse image of L minus the origin, and then you close it. So this is what's called the strict transform. So if this is L, this will be that, and you do it for two lines, they will become disjoint. Somehow, in the central CP1, the point remembers not only the line, not only the point that it's over the origin, but which direction the line came into that point. Of course, this holds for lines, but it equally works for submanifolds intersecting transversely. So by blowing up, we can arrange that things which intersect downstairs in X might become disjoint or might intersect in less points in the blow. That's the whole point of it, from our perspective. Okay, so let's take a particular example of this whole story. Let's take a very simple one. CP2 point L, just like in my previous picture, we have all the lines passing through this point P. These were my LTs, if you remember. T comes from CP1. This is not a fibration. It became a fibration, was a fibration over CP2 minus a point, minus P to CP1, because P wanted to be projected to all the points of L. That's like not possible. But if we blow up P, then we get a fibration. But of course we change the four-manifold, so we get from CP2 connected some CP2 bar, as I mentioned or remarked over there. This is a sphere bundle, CP2 bundle. It needs a little bit of a thinking to show that it's the non-trivial one. For example, we can construct a section of that bundle. And now, for a change, I will use this. We just take L prime, which is just another line not passing through P, L prime, and that will be a section because it will intersect every fiber exactly once, and it will intersect the zero section exactly in one point, as any two lines, distinct lines in CP2 intersecting one point. So you just see that This is the non-trivial bundle with Euler number 1 over CP1. Okay. Well, that's not a very exciting example, so we will try to work out a more exciting one. And so instead of taking lines in CP2, we take other degree curves. So next example. Consider C0, C1, two cubic curves. Defined by P0, P1, degree 3 homogeneous polynomials. Okay? So I considered linear, degree 1, and now we jump to degree 3. So if you are really interested in this story, try to work out what happens with degree 2, and you will find something interesting. I mean, this is just P0 inverse. So if you have two curves, CP2, C0, C1, there is this theorem of Bezout that if you have two degree 3 curves, that they intersect each other generically in 9 points. They intersect each other with multiplicities exactly 9 times. If you pick them generically, then they will intersect exactly 9 points. So let's assume that. Later we will just relax that. But so we have now 9 intersection points where the multiplicity of the intersection should be 1, so these are transverse intersections. In the blackboard that you see only 3, but you should see 9. Okay? And now we just do the following. So consider CT, where T is a projective parameter, T0, T1 in CP1, which is just the inverse image of 0 for the polynomial PT, where PT is just T0, T0 plus T1, T1. Okay, so these were 2 degree 3 polynomials, and now I take a linear combination of them. It's still a degree 3 polynomial. And so I have a whole collection of CTs, these are curves. Notice that when T0, when T is 1, 1, 0, then I just get P0. When it is 0, 1, the infinity in CP1, then I get P1 back. And so it just sort of gives us a whole bunch of curves covering the CP1, CP2, exactly like the lines covered in before, right? You just pick a point wherever outside of these intersections, and then you can solve for T0 and T1 the equation PT should be, and Q should be equal to 0. That is a linear problem, and you can come up with T0 and T1. So there is a unique guide which passes through every point, except the intersection points where every curve passes through. If P0 and P1 are 0 at the same time, no matter what parameters we put here, PT will be always 0. So we are facing exactly the same problem, except now, instead of one single problematic point, now we have 9. So we have so we have a function from CP2 minus C0 intersection C1 to CP1 associating the projective parameters to Q, which is determined by this equation. So far so good? Okay, and then we can do the previous trick, blow up C0 intersection C1 and get a map CP2 now 9-fold blow up to CP1. Okay, so that's fantastic. What are the fibers? Well, a typical fiber should be like a cubic curve in CP2 after you blow up in 9 distinct points. And I didn't say that, but the way this formula works is that we can take the complex curve, which has exactly that genus, and then the proof is that no one can have smaller genus than the complex curve. So for d equals 3, I hope it will just give you 1. The fiber, the typical fiber, is of genus 1, so called the torus. Well, could that happen that every fiber is a torus? That would be fantastic. We have a torus fibration over CP1, but that's very questionable. What happens? So let's compute the Euler characteristic. If you have a fibration, the Euler characteristic is multiplicative. If all fibers are tori, then we get, for the total space, we get the base has Euler characteristic 2, the fiber has Euler characteristic 0, so this would be 0. On the other hand, we know that this Euler characteristic is 12. So that just means that although C0 and C1 are smooth, nice tori embedded in CP2, when we take this whole one parameter family, we should need some kind of singularity, some degenerations. Actually, if we consider the easiest possible degenerations, then we have to have exactly 12 of those. So there are singular fibers in this fibration. So, what? Yeah, the generic one, say the C0 you start with and C1 you start with, they are tori. Because you are free to pick these two polynomials and you pick them in a way.
Okay, you could pick them to be tori.
Yes, and you do.
And you do.
And then you take this whole family.
Yes.
And what I would like to convince you about is that although you started with two smooth guys, but when you take this projective line worth of cubic curves, you cannot arrange it in a way that everybody is a torus. There will be degeneration. There must be. Now we will not discuss the degenerations, we will do that in my fifth lecture. But I just want to plant the idea that, you know.
And you said there were fibers to this.
The fibers are exactly those.
So every T, yeah. So these are your CP1 is your T, and so a fiber
Yes.
is a PT.
A fiber is one of the CTs blown up in 9 points, but 9 distinct points. Their topology doesn't change at all. Right? Very similarly to when I did this lift of the line, you know, I deleted 1 point, but then I added back the point corresponding to actually the line, you know, where it passes through the CP1. So the same happens here. The topology of these guys don't change at all. So if we were so brave to assume that all the fibers are tori, then we would get a contradiction. Unless, of course, 12 would be equal to 0. No. Does that make sense? So there is something interesting going on, and we will discuss that a little bit later. Okay. With that said, this is a fantastic four-manifold together with a fibration. It's called the rational elliptic surface. Elliptic surface refers to the fact that it is fibered by elliptic curves, which are, you know, cubic curves on CP2 are called elliptic curves, and it's a rational surface because it's CP2 blown up in some points. From that single example, we can now construct a whole family of other four manifolds by the following trick. I will also introduce the notation E1, elliptic surface, and first in the row. And let's construct E2. And for that, I will try to do some pictures. So as you might guess, E2 is constructed from two E1s. So these come with this fibration, these maps, where the generic fiber is a torus. But not all fibers are tori. There are some singular fibers, and now we sort of disregard them. We try to keep ourselves a little bit further away. We just pick a generic fiber, and we take the tubular neighborhood of that fiber. So this fiber maps to that point. I take a little neighborhood of that point down in CP1, and take the inverse image, which will be D2 cross T2. So a disk worth of T2s. Okay? And likewise here. I do exactly the same. I do it twice. And now I delete this copy and I delete this copy, so I will get two four manifolds with boundary. So this is now E1 minus the interior of D2 cross T2, and the same here. So here interior. Okay, so these are two four manifolds now with boundary. The boundary, of course, is the same as the boundary of this little neighborhood, which is just the three torus. So these are three tori. And then I identify the two boundaries. In order to have an oriented four manifold, what you need to do is to use an orientation reversing diffeomorphism between the boundaries, right? That makes perfect sense because what goes in here should come out there, so you need the orientation reversal. And the map should be the identity on the T2 factor cross, so this T3 is a product, fiber cross the base S1. And it should be identity on T2 conjugation on the S1 factor. So it's like a, complex conjugation. So this is orientation reversing, this is orientation preserving, so together it's an orientation reversing. So when we plug them together, fiber goes to fiber, so the old fibration survives. The singular fibers which were here and very ugly and we don't know at the moment, they just survive and they are still there. So at the end of the day, this gives us a bigger block, which is now glued along with T3, and it maps down to CP1, and this is what we call E2. So far, so good? I mean, good or not? No, that's what we do. And of course, this brings in a new idea that we had two copies, but of course we can repeat this process. All we need is two regular fibers and then taking their small tubular neighborhood, so we can just repeat it many, many times. So this procedure has a name, and it is called the fiber sum. And we denote it by the good old sharp together with an F, that we use a fibration and the fiber sum. So E2 is just the fiber sum of the two elliptic fibrations on E1. And then here is a definition. En is just the fiber sum of En minus 1 with E1. So we just keep repeating that process, and we have now an infinite family of four manifolds which I consider interesting. I wrote my PhD thesis about elliptic surfaces, so that's something I like. So here is a remark, which you don't have to see at the moment, but this E2 is actually diffeomorphic to my S4 earlier. You remember, this is the K3 surface. And we will get other presentations of the same surface. The K3 surface is interesting because it can be constructed in so many different ways. And I used to tell to my students that, four manifolds were created in the last day of creation. God was tired and made all kinds of mistakes, which tried to rectify by making SO4 not simple and stuff like that. And the major mistake was the K3. This is where everything went astray. That it has so many constructions and it has so many, it sort of encapsulates all the complexity of four-dimensional topology, in my view. So we have to face some mistakes. God did. So this will be a recurring theme. To come back to the K3 surface, I will not prove that these manifolds are the same. Actually, what happens is that if you have a four-manifold, which is a complex surface, it's simply connected, and the first term class is 0, they are all diffeomorphic. So the characterization is that complex, phi1 trivial, C1 0, they are all diffeomorphic. They form a big family of complex surfaces. These are very interesting, and we will study them on and off in these lectures. Okay, so here is a claim which is very easy to prove, and I will not do that. To compute the characteristic numbers and the fundamental group of these objects. I mean, this is what you have to do when you meet a four-manifold. It's like, when two dogs meet, they sniff each other. This is how we sniff four-manifolds. You check the fundamental group first. It turns out to be trivial. It's just a simple application of von Kampen's theorem, because what you have to understand is that these complements are also simply connected, because you have, but you have to check what happens with this normal circle, and the normal circle bounds a disk in the complement. It's exactly the blow-up. The blow-up sphere, you replace a point by a sphere which will intersect every fiber exactly once. So that's sort of an easy exercise. Oops. I also mentioned that the Euler characteristic is easy to compute. It's sort of additive in four-dimensional topology. So if you compute that, I hope you will get 12n. The signature is not bad. This is again additive. That's a little more complicated, and you will get minus 8n. And the parity is that even if n is even, and odd if n is odd. I mean, this sentence looks really stupid, but what I mean is that the manifold has an even intersection for exactly when the number n is even, and likewise it's odd. Okay, so we have now a collection of manifolds. They are all distinct. They have different Euler characteristics, different signature, but they will be sort of the building blocks for me to create interesting exotic manifolds. A little problem, if you want to think about it, what is the intersection form? How do you express the intersection form of En in terms of the basic blocks, what I told you? 1 by 1 matrices, 1 and plus 1 and minus 1, and the E8 and the hyperbole. It's clear that they are indefinite, because B2 is 12 and minus 2. It's simply connected, so the first Betti number and the third Betti number are 0. There is a 0th and the 4th. So this is the B2, but the signature is minus 8n, so definitely they are not definite. Indefinite, and we know the classification for indefinite values. Okay. A particular question I would like to return towards the end of the lecture series is, well, what self-intersection spheres do we find in K3, K2, and in general in EN. So I try to convince you that it's very important to understand what are the surfaces in four-manifolds, and this is probably the simplest version of that question. I give you one particular four-manifold, what are the embedded spheres? I'm not even asking that. What are the self-intersections of embedded spheres? It's a very well-posed question, and as I will indicate, we do not know the exact answer for that. Okay. Since we are talking about submanifolds, let me just give you another example, which you will be interested in later on. And this will be out of the blue at the moment. So let's take X to be the four-dimensional torus. So this is just two tori multiplied together. I usually like to draw them like this. So this is a T2 and this is a T2. What you have to see immediately is like 6 two-dimensional tori in that four-manifold, right? So 6 tori in T2, which is just S1 plus S1 plus S1 plus S1. These two torus is the product of the first two. These two torus is the product of the last two. But there are 4 others. We can take first against the third, first against the fourth, second against, and so on. So there are like 6 tori intersecting each other as follows. If you take the complementary indices, they should intersect each other in one point. Right? When I say that you take T2 as the product of the first two, what I really mean is that we freeze the coordinate here to be P, and here some P prime, and then we take S1 plus S1 plus P times P prime. So the complementary indices, tori corresponding to complementary indices, intersect each other in one point, and the others are disjoint. So this is my usual picture. There is a T2, there is a T2, and there are 2 intersecting like this. Does this make sense? Unfortunately, I have to draw dimension-reduced pictures. I'm sorry for that. I'm really bad in drawing in 4 space at 2-dimensional surface. But so I hope you understand what I mean. So this is S1 cross S1 cross point cross point. This is point cross S1 cross S1. And this is like S1 cross point cross S1 cross point. Shall I write it down?
No. So they are the ones that cross as a point. Yes. And then you're saying the other ones you can choose.
You can choose them to be disjoint.
Because you have an extra S1 free.
Yeah, so they have a common frozen coordinate, and you can just pick different points on that particular S1. Right? Okay, so we see a lot of guys. Indeed, age lower 2 of T4 is just Z6. That requires a little bit of a thinking, not much, I should add. Okay, so here is this torus cross a point. And just to indicate that somehow the genus function is not that simple as you might guess, not like the Thurston norm in 3 manifolds. Now we take this homology class. So this is an age lower 2 T4. And let's take twice of that class. And I would like to show you that this can also be represented by a torus. So for this one, we have to think. That's very unfortunate, but this is what we do. So how do we see one of these tori? So I would like to draw a little neighborhood like D2 cross a torus. So sorry, maybe torus cross D2. This is a little neighborhood of this torus, which I view as S1 cross D2. And the torus is just the core circle in this solid torus cross this S1, right? But we can make a trick. Instead of taking the core, so here's the core circle, we can take a two-braid. So forget about that. Take a two-braid in S1 plus D2. So inside the solid torus, I take an embedded circle which wraps around twice and cross it with S1. This will give me this homology class, but it will be still a torus. It will be still a circle times a circle. In fact, this can be promoted to any n by not taking a two braid, but an n braid. You know, it just wraps around n times embedded, and you just take the product with S1, and then you see that somehow things are a little more complicated. So these homology classes are multiples of each other, but the genus of the surface representing them is always the same. Of course, we are taking minimal genus, so in principle, you could imagine that they can be represented by a sphere that would be even lower of a genus, and I will leave you to decide whether there are homologically essential tori in T4, homologically essential spheres in T4. If you don't get the answer that there are none, then start over. Yeah, that's okay. I think my time is up, so let me just check. Yeah. So both these examples and that particular torus will play some role later on, but they also serve as examples in surfaces in four-manifolds, and this will be somehow the direction I would like to take in the next couple of lectures. But this is for today. Thank you very much.